So in terms of reminders, the Positive Physics Unit 12 assessment is what's going to be your semester exam. So be keeping that in mind. And to review for that, it would be great if you go through the AP Classroom Units 1 and 2. You want to click on the Assessments tab, and you'll be able to access the multiple choice questions. And then Positive Physics units, we've mostly covered we've covered all of 1 through 5. After today, we'll have covered most of 6 and parts of 7, a little bit of 8 and 9. We're going to focus more on those examples on Monday and Wednesday next week to really kind of pull things all together and finalize everything. But I would encourage you to go ahead and begin practicing on those websites to prepare for the exam. The exam will be, as we talked about, Tuesday, December 15th. So 2 weeks from, almost 2 weeks away, not quite 2 weeks anymore. And you'll have a 3-hour window from 8:30 a.m. to 11:30 a.m. And you'll be taking it live. You have to get the whole exam done within that 3 hours. When you're done, you're free to go. It's 30 questions, and it's just the same positive physics style questions. If you finish it all and have time to go back and do corrections, you'll obviously be checking your answers as you go. You can finalize it and go back in and do corrections, and your score will be the average of the original percent and your corrections percent. Yeah, Andy?
So whenever I was doing the other positive physics like assignments, I mean for the assessments, I would like if I got stuck on one, I would go back to the work and then like go over those questions. Are we allowed to do that on the test or?
Yeah. I mean, I would encourage you to try to do that beforehand and maybe take notes on the ones that you found tricky so that you're not trying to get all of that done in a 3-hour period where you've got the pressure of the exam. And the exam's 25 or 20% of your grade. So you want to make sure that you're, not just seeing those questions for the first time, hopefully at that moment. But yeah, you can go back and forth. The only limitation will be, I'm going to ask you, well, I guess it won't really help, but you have to get it done in that 3-hour time frame. So.
Wait, so we are allowed to, like, during the 3-hour exam, go back to the work and, like, do some and then go back?
Mm-hmm. Yeah, there's no way for me to know whether you are or not. So it's just going to be available for you you have 3 hours to get that done. I won't unlock the assessment until then, so you won't know your exact group of 30 questions. But if you go through the whole work section, except for the purple highlighted ones, you should have seen all the questions beforehand. You just won't know exactly which ones are going to show up on your version. But yeah, you can, in that 3 hours, you can use the site, you can use even your notes and stuff. It's, there's no way for me to really control that in a remote setting. So, I mean, I could ask you to and just trust that you will, but rather than hoping some will and knowing maybe some might not, it's, I think, just fairer to just say, you got 3 hours, you got to get it done. Yeah, good questions. Anything else you want to ask about that?
So it's open now?
Yeah.
Okay.
Okay. So that's a good quick review for that. Today, we're going to try to go through systems and learn about dealing with systems of objects and how forces behave and how we can think through net force with a system, and then also break the system down into parts. So that'll be the beginning. And then we're going to talk about friction. So that's basically units 6 and 7 on positive physics that we're going to be trying to cover today. Not every possible question, but a lot of coverage there. So that's our goal for today. And then whatever time we have left, whether it's 10 minutes or 30 minutes or whatever it ends up being, you'll have that time just to begin reviewing for the exam. No new assignment today. All right, so the first problem I'd like to go through with you is this problem. This is what's called an Atwood machine. And normally in class, I have one set up that covers the whole width of the class, but obviously we can't do that remotely. But the basic idea is we've got 2 objects connected by a cable or a rope or string of some sort. And I'm just kind of going back and forth so you can see the animation multiple times, because I know the internet being slow, you're probably seeing it all at different times and different ways and maybe kind of choppy. But basically what we're saying is if we held these 2 objects still and then let go, it's obvious that because the one side has a 3 kilogram mass hanging from it, the other side's going to accelerate up and the green side's going to accelerate down. So we can know that that's what's going to happen. And what they're asking us to do here in this Atwood's machine question, which is very common kind of a question, is to determine what is the acceleration of these two objects. How much is the orange one accelerating? How much is the green one accelerating? And then what is the tension in that single string? So the string just goes over the pulley and then down to the other. It's just a single string connecting the two that's just laying on top of a pulley that rotates. Now, one thing they have not put in this question, but College Board usually does, is they will usually say, assume the string's mass is negligible. And what that means is the mass of the string compared to the mass of those objects is so slight that it's not going to affect the outcome. Now, when I actually set up the Atwood's machine in the classroom, we show how if you have a small enough weight on each side, when you get a whole bunch of string on one side compared to how much string is on the other side, it actually does matter. So we kind of prove that that is not necessarily the whole story. It's kind of like when we say ignore air resistance. We're not saying air resistance doesn't exist. We're just saying it's probably small enough that we can ignore it. And generally speaking, if I have a 3 kilogram mass and a 2 kilogram mass, those are heavy enough. The string's mass is not going to make a big enough difference that we would probably even notice it. But what I illustrate in class is sometimes we use just like a 2 grams on one side and 2 grams on the other side. So it's, you know, thousands of times smaller than this. And we see that actually in that case, when you have really small masses, the string's mass does make a difference. But they never ask you to account for the string's mass. So you'd see that phrase and it's not here. So I want you to have heard it before so you don't get confused by it. So if they say you can ignore the mass of the string, they're just saying, just focus on this 3 kilograms and 2 kilograms. Don't worry about the string itself. And then they also will usually say it's a frictionless pulley. And they'll often usually say, or almost always usually say, and you can ignore the mass of the pulley. Now, the reason that they give you frictionless pulley is probably pretty obvious. If you're accounting for friction, then you got to figure out, okay, well, how much is that going to slow down the turning of the pulley? And we could do it after we do some more things next semester on rotation. But for now, we don't even know how to do that. So that's why they'll usually say frictionless pulley at this point. And then the mass of the pulley, that pulley is going to actually accelerate in a circular motion. And so if it accelerates, there has to be a force. And the pulley, if it has significant mass, would require a greater force to overcome its inertia. And so what they're basically saying is this pulley is frictionless enough, you don't need to worry about it, and its mass is light enough, you don't need to worry about overcoming its inertia. And that is generally how they'll phrase these questions. So the book didn't make those special indications, but College Board almost always does. And for now, we couldn't answer the question if they didn't say those things because we don't know about rotational motion yet. That's next semester. So those are a couple things you'll notice when you read a College Board question like this. So if you're practicing some of the ones on the AP Classroom site, it'll usually have those phrases. And then the second part of the question, after we've calculated the acceleration and the tension in the string, could it be possible that this 2 kilogram object would actually be lowering, going downward first, and then switch directions and go the other way? Is that even possible? And so we're going to talk about that at the end once we've thought it through a little bit. So any questions about the scenario before we start digging into the math and how we actually solve this? All right, how many forces are acting on the orange 2 kilogram box? See a couple peace signs. Yep. There's the upward tension in the string, and there's the weight caused by the gravitational force field of the Earth. How many forces are in the green 3 kilogram box? Same 2, right? Tension pulling up in the string and the weight because of the gravitational force of the Earth pulling down. So the first thing we want to do is identify that. What are the forces on these two objects? Probably even draw some sort of either force diagram or free body diagram to evaluate it. We know the tension is up and the weight is down. There's no set formula for tension. The way you find tension force is by combining the net force concept and figuring out the missing piece, basically. But we can calculate the weight because the weight of an object is just mass times the acceleration due to gravity. And here they're just using 10 as the acceleration due to gravity. And you'll notice right now they're not really focusing on the fact that weight is down and putting a negative sign on it. They're just finding the absolute value of it for the time being, just to make sure we remember, okay, the weight of the orange box would be 2 kilograms times 10 meters per second squared. And the weight of the green box would be 3 kilograms times 10 meters per second squared. So we've got a 20 Newton weight of the orange box and a 30 Newton weight of the green box. Questions about that step, just thinking through what the forces are and how we calculate the weight of each. All right, so if I was holding these so that they didn't move and I let go, which way should they move? Towards the green side or towards the orange side? Like, which way would it rotate?
Downwards on the green side.
Yeah, it's going to rotate. That pulley is going to rotate, and the green side is going to go down. The orange is going to go up, right? We can predict that because there's a greater weight on the right where the green box is at than on the left where the orange box is at. Now, the way we figure out the acceleration is to consider, instead of this being two different objects, to consider them as a single system. And the reason we can do that, if we change the diagram and just draw it out as, okay, the force is pulling the orange in one direction, but the weight is pulling it in the opposite direction. And the tension force is pulling the green one in one direction, but the weight is in the opposite direction. But the tension in the rope is going to be the same throughout. It's just one rope, one string. So that tension force, the orange one is creating a tension force one direction, the green one is creating a tension force the other direction. Those two would be, you could say, internal to the system and equal and opposite. So really, those two tension forces, when we think about it as a whole system, cancel each other out, because the green's creating tension one direction, the orange is creating tension the other direction, and it's going to be the same because it's one string. And it may be weird that it creates the same tension when we have two different weights, but that goes back to Newton's third law. Whatever force it's creating in one direction with one object, it has to create the same in the other direction with the other object. So that tension is going to be felt by the string. If the two was being held, then there would be another force. But if we're allowing them to move, then that tension force in the string is equal all the way through the string, because both the orange one and the green one are going to accelerate at the same time if we're letting it go. So if we think about it as a system, the green one can't move unless the orange one does too, and the orange one can't move unless the green one does too. They're connected by this string. So when one moves, they both move. And so therefore the tension in the string is the same. So knowing that the tension in the string is the same and cancels out, what's the net force?
10 newtons.
10 newtons, and it's going to be towards the green side, right? Which is what we predicted before. It's going to rotate and the green side is going to go down. It's going to pull the orange one up. Now we're just kind of thinking about it as a system. We're basically saying those tension forces cancel. So we really just have a 20 Newton force to the left, 30 Newton force to the right. And the system of objects is just a 5 kilogram object if we think about them as one system. So our net force is just 10 newtons to the right or to the green side. So we're sort of simplifying some things down here to think about it as a system, but as long as we understand why we can do that, it gives us some nice advantages, because now we know the net force of this entire system is 10 newtons. We know that the total mass of this entire system is 5 kilograms. If we know the mass and we know the force, how do we find the acceleration?
Divide the force by the mass.
And what law are we applying there?
F equals ma, the third law.
Close.
Second.
Second law, yep. Applying that second law.
I never remember the numbers.
Yeah, that is actually something. With the kinematics equations, they're not formally numbered, so you don't really need to remember those. But technically, for the Newton's laws, sometimes they expect that you do remember which one is the first and which one is the second, which one is the third. So you do want to probably try to get that committed to memory at some point. I know you're still learning it for now, so it's not a big deal, but it's technically the second law. It's that relationship that shows us the proportionality of mass and force to acceleration. And we know the net force now. We've kind of thought it through. It's 10 newtons. And we know the mass of the whole system is 5 kilograms because they would both have to move, not just one. And so 10 newtons divided by 5 kilograms tells us as a system, they would be accelerating 2 meters per second squared. Now, obviously, the green one's going to be accelerating downward and the orange is going to be accelerating upward. So the direction of their acceleration is different, but the magnitude's the same because the green can't move without the orange moving and vice versa, right? So they have to move in the same way in conjunction with each other since they're connected.
Just out of curiosity, what would the tension force be? Like 25 newtons?
We're going to figure that out in the next slide. Good question. So the first part of the question was, what's the acceleration? If we go back, just to remind you, there were 3 questions actually. So 1, find the acceleration of the objects. 2, what's the tension in the string, or B. And then 2, could it have been moving downward on the orange side and then go the other direction? We'll cover all of those things. So right now we've answered the first part. We know the acceleration of this system is 2 meters per second. The green one would be accelerating down at 2 meters per second. The orange one will be accelerating up at 2 meters per second squared. All right, any other questions so far? All right, now to figure out the tension in the rope, it's much easier to not think about it as a system. To find the net force and the net acceleration, it is easiest to combine it together, think about what cancels, and think about it as a whole system. But to find the tension, it's much easier if we just focus on either the orange one or the green one. And it doesn't matter which one we pick because they'll both give us the same answer. We'll kind of prove that. You don't normally have to find it both ways, but we'll just show you that both ways give you the same result. So let's do that. If we focus on the orange one first, the one on the left, we know that that one just has 2 forces on it, the tension pulling upward and the weight pulling down. And we know that it would accelerate upwards, so the tension must be larger than the weight. And we found from our previous problem, when we thought about it as a system, it will accelerate at 2 meters per second squared in that upward direction. So thinking through Newton's second law on just the orange object, we know the net force can be solved 2 ways. It's technically a system of equations. The net force is mass times acceleration, which would be 2 kilograms times 2 meters per second squared. So we know it that way. But the net force would also be the vector sum of tension and weight, just those 2 things added together as vectors. So it's a system. We know to find it with mass times acceleration one way, and we know to find it as adding those 2 other forces together as another way. Since they're both equal to the same thing, we can use it as a system and say, oh, the vector sum must equal the mass times acceleration, because both of those things equal the net force. So you can see the substitution they've done here. One way to find the net force is mass times acceleration. They've shown it on the right. The other way is to find the vector sum of the 2 forces, the tension and the weight. The weight's downward, -20. And so if we add the 20 to both sides, we can see the tension force would be 24 newtons in the upward direction. And that makes sense. If the orange one's going to accelerate up, the tension force must be larger than the weight. Questions about that process? All right. We can do the same thing with the green box. And again, you don't really need to do both, but I just want to show you how you can and how you get the same answer either way. It's a way you can check your work if you want. So if we think about the green object, it is accelerating at 2 meters per second squared also, but downward. And its weight is larger, 30 newtons, and its mass is larger, 3 kilograms. But the same relationship exists. One way to find its net force is mass times acceleration, 3 kilograms times 2 meters per second squared, but now down. And another way to find the net force is the sum of those 2 vectors, the tension going up and the weight going down, and just adding them as vectors. So 2 ways to find the net force, we just set them equal to each other. And so we've got the tension plus the weight as vectors is going to equal the mass times the acceleration. And if we find that net force on the right side, it tells us it's going to be a -6 newtons because it's going to accelerate downward. And if we add the weight to both sides to solve for Ft, we find out same thing. The tension in the string for this side of the pulley is also going to be 24 newtons. So whichever way you choose, you should get the same result. Any questions about this? We basically done the A and the B. We found the acceleration, and then now we found the tension in the string. All right, now the second part, that number 2, this is something, again, if we were in class, I would have this. It's an Atwood's machine I create that stretches the width of the room across the shelves. And we actually do test this. Could I pull on the orange one to make it start to fall? And would it still work? Would it slow down and then reverse direction and go back the other way? Is that possible? It is possible. We actually demonstrate it normally. Can't really do that remotely very easily. Even if I were in my classroom and had it set up, it covers the whole width of the room. So you'd be so zoomed out, you couldn't really see what was going on. It's one of those things that you really need to see in person. It might be something we demonstrate. In fact, it would actually be a good demonstration the first day back to help us think about a couple things when we get back on campus in January. But the way to think that through, could it have been moving the other direction? Could the orange one have been going down and the green one going up first? Is that even possible? And it is possible. Could I get someone to read this slide for us to explain how and why it's possible?
I'll do it.
Thank you.
Answer, yes. If the objects were released from rest, then the 2 kilogram object would then always be moving upward until it hit the wheel. However, if the 2 kilogram object had been given an initial tug downward, then it would move downward and then upward. Interestingly, the values we found for acceleration and tension will remain the same for the upward and downward motion. Note that nowhere in our calculations did we consider the direction of the velocity.
So it wouldn't happen naturally. There's no way naturally the green one would go up and the orange one would go down. But if I provided another external force by tugging it, I could make it go that way for a little bit. And then eventually that 30 newtons on the right green side is going to start pulling it back the other direction. So it is possible, but it would require another external force. Any questions about that? All right, we're going to go through one other system question. And if you're wanting some extra practice on system problems, obviously you can go to Unit 12 on positive physics, and it has a little subsection on that. But if you go to Unit 7 on positive physics, that whole unit is about different kinds of systems. We're just going to do one more today, and then we'll do multiple more next Monday and Wednesday. But I just want to cover one more today for you. This one is similar. It's another kind of Atwood's machine. Basically, an Atwood's machine is whenever we have 2 masses connected by a string, or sometimes even more than 2 masses, connected by a string and passing over at least one pulley. Sometimes there's multiple pulleys, sometimes there's multiple strings, sometimes there's multiple objects, but the same idea is that you've got this system of things moving and they're all connected by strings and there's pulleys, and so we'll look at a variety of different kinds of problems together, but this is another one. You can see the difference in this one is the 3 kilogram, they're using the same 2 weights here. The 3 kilogram green one is just being pulled down by gravity, but the 2 kilogram one is actually sliding across a table. And you can see what they're asking us to calculate is how much is the acceleration again of these 2 objects. And because they're connected, if we let them go, they'll have to accelerate at the same rate. The green one can't accelerate faster than the orange one and vice versa. They're connected, so they would have to accelerate the same rate. And they're also saying we can use 10 to simplify the math instead of the 9.81. And we can also ignore friction. We haven't really learned how to calculate friction yet. That's going to be in the second half of today's lesson. So for now, we're just going to pretend that this is so lubricated or so slippery that the friction is negligible. Not that it doesn't exist, it's just so small it won't make a difference. And then the second thing, just like we did before, once we figured out the acceleration, what's the tension in the string? So that's what we're trying to figure out. So how many forces are acting on the green 3 kilogram box? Seeing some hesitation. A couple people are saying 2, a couple people are saying 3. Some variety here. So there's weight, right? Pulling it down because gravity is going to be pulling it down. There's the tension pulling it up. Is there any other vertical force besides the weight pulling down and the tension pulling up? Okay. And then is there anything pulling the 3 kilogram object to the side at all? No. So there's just 2. It's just the downward weight by gravity and then the upward tension. So the green one can only move up or down, right? It's not going to move sideways at all. It's just going to move up or down based on whether those 2 forces are balanced or not. If we held on to the orange one at the top and didn't let it move, then those would be balanced, right? Because the green one couldn't move in that case. The weight and the tension would be equal. But as soon as I let go of the orange one and let it slide, then they're not going to be balanced anymore. And the green one will start to accelerate downward. But it won't accelerate at negative 9.8 meters per second squared because that orange one's going to be holding it back a little bit, right? So while gravity will still be pulling it with that same gravitational acceleration, in its actual movement, it won't be accelerating that fast. It'll have a slower acceleration. All right, how about the orange one? How many forces are acting on the orange one? I see a couple votes for 3, a few votes for 3, some more votes for 3. Okay, the number's rising. Yeah, we've got the weight down. What are the other 2?
Normal and tension.
Normal and the tension.
Yeah. So if we think about the forces here I've got the free body force diagrams drawn. I guess they're not technically free body, but they're close. We've got the orange one with its weight going down and its normal force going up. And the normal force and the weight force should be equal and opposite on that orange one, right? I mean, we shouldn't expect that orange block to fly up into the air or dig down into the table at all. We would assume that those should be balanced. It should just stay right on the surface. However, there's a tension that's going to cause it to slide to the right. And the tension causing the orange one to slide to the right has to be the same as the tension that the green one's creating by falling because of gravity. So we've got the 2 forces on the green box and the 3 forces on the orange box. But 2 of the ones on the orange box cancel out. We know the weight of the boxes would be the same as before, 20 newtons for the orange one, 30 newtons for the green one. If we think about it as a system again, though, so when we draw the system, we can draw it in any shape or form we want. We know that the normal and the weight force on the orange box are going to cancel out. We know internally the tension going to the orange box and the tension going to the green box is going to be equal because it's just one rope. So that tension will be the same throughout. So the green box has only one force pulling on it, and the orange box has only one force pulling on it. I think we have a question here. Let me see what the chat is. I think it said on the previous slide, we're going to ignore friction. So here it just says negligible friction. So if there was friction, then we would have to draw another force. And that'll be something we will do next week. But we haven't learned how to calculate that yet. That's actually later today. But so if we are ignoring friction, then these are the only forces. And so as a system, the 20 newtons up and 20 newtons down cancels, the 2 tension forces cancel. And so that 30 newtons to the right, basically, it's not really directed to the right, but in our picture, it's going to the right, is going to have to pull all 5 kilograms. That 30 newtons of force that's not being canceled by anything else net is going to be what accelerates that orange one and green one together. So if we just looked at the green one, we would have to think about the tension. If we just looked at the orange one, we would have to look at the tension. But if we combine them together, the tensions cancel out. And so all that's left is the 30 newtons to the right in this picture, really 30 newtons down. But so then if we know that's the net force and we know the whole system is of 5 kilograms, this acceleration will be 6 meters per second squared. So now we've answered the first part. Any questions about any step we've taken here to find the acceleration? So if we try to think about the orange one and the green one separately, you can solve the problem that way, but you end up having to do systems of equations and lots of substitution, and it's far more complicated. It's not impossible, but it's not easy. If you just think about it as a system and recognize that those tensions would be equal, and it's just that 30 newtons going to be pulling the whole thing, it makes it a lot easier. You can solve this problem in just minutes instead of many, many minutes. All right. So now we have to find the tension in that string, and it's going to be the same for both the orange one and the green one. So vertically for the green one and horizontally for the orange one, the value will be the same. We could solve it either way. We'll show both again just to prove that they're equal. And so let's take a look at each of those separately. If we just redraw our picture here, we now know the acceleration. The orange will be accelerating to the right at 6 meters per second squared. The green will be accelerating down at 6 meters per second squared. If we focus just in on the orange one first, the net force of just the orange one, not the whole system, but just the orange block, is just the tension, because those two vertical forces do cancel out. So if we focus on just the orange one by itself, tension is the net force. And if we know that that is the only force, and we know the mass is 2 kilograms, and we now know it would have to be accelerating at 6 meters per second squared, that tension must be 12 newtons. For the green one, it has two forces that we have to account for. For the orange one, there were 3 forces, but 2 canceled out. So only the tension made the net force. But for the green object, we have to account for both the weight and the tension to figure out what the net force would be. So this one we're going to treat much more like we did in the previous problem. We're going to say, well, the net force can be calculated 2 ways. It can be just Newton's second law, mass times acceleration. We know the mass is 3 kilograms, and we know the acceleration is 6 meters per second squared, but down now. And it can also, the net force can also be calculated by just adding those vectors of the vertical tension and the vertical weight. And we just add them as vectors and find the net force that way. And so the tension added to the weight as vectors has to equal the mass times the acceleration value. And so mass times acceleration gives us negative 18 newtons. The weight would be 30 newtons downwards. So when we add that 30 to the other side, we get, again, a tension of 12 newtons of force. So same value, whichever way we calculate it. A little bit easier to calculate it from the orange one this time, but same result. Questions on this one? Well, Kate earlier asked about friction. If there was friction, we would just have to add another force on the orange box, and then we couldn't know this net force quite as easily because it wouldn't just be the tension. We would have to take the tension plus the friction that's counteracting it. So it's not really that much harder. It's just one extra step. And we'll practice some like that next week. All right, so the next kind of problem we're going to start, actually we're going to save this for next week, but just so you can get a preview, we're going to start talking about what if those forces are at angles, and you can probably already start to predict, oh, if there's an angle, we're going to have to use some trig, we're going to have to find out the horizontal component, we're going to have to find out the vertical component, and so we'll break this one down on Monday. But for today, I also want to talk about friction, because obviously if we just keep saying ignore friction, ignore friction, ignore friction, most systems we can't really do that. Most of the time friction is significant enough that ignoring it's not practical. We're going to get a very errored answer. And so I do want to go ahead and explain how we can calculate friction. And I have these notes in Smart Notebook instead of PowerPoint. So I like this curriculum a little bit better for explaining friction. So you guys are all familiar with friction. And if you think, I mean, if you rub your hands together, you know that there's friction, you feel the heat that's generated. If you're trying to slide a dresser across the floor, you know that there's friction that makes it hard. And you know if the dresser's really heavy, like if all the dresser drawers are full of heavy stuff, it's harder to break that friction. And if all the drawers are empty, it's easier to break that friction. So you know the weight has something to do with it. I mean, just by your practical life experience, you have some knowledge about friction. But technically, the way we calculate friction is not based exactly on the weight, we actually base it on the normal force. So I want to focus in and just quickly review what is that normal force. It's the other half of the force when we think about weight and support of an object sitting on a surface. So if you recall from before, this is just a review real quick. I think before it was a cat sitting on a table. Now we've got a vase, but the same idea. The weight will always be down, straight down to the center of the earth, and the normal force will always be perpendicular to the surface. So for now, today, we're going to focus on flat surfaces. I will give you a little glimpse into an angled one later, but we'll mostly focus on just flat surfaces where the normal force and the weight force, since they're directly up and directly down, as long as the object's not rising or falling, they should be equal. And so whatever the weight of that vase is, that's how much normal force the table has to supply. So again, it's perpendicular to the surface. And like you can see here, the normal force is exactly as large as needed to balance the force from the object. If the required force gets too big, something breaks. The word normal and perpendicular are synonymous in this context. So just like in math, we say normal means perpendicular, it also is perpendicular here. So on my desk, it has to be able to hold my computer and my calculator and my mouse. And apparently it can, because my desk is not breaking. And I know I've stood on this desk before to change the light bulb up above, and it didn't break when I stood on it either. So apparently it's capable of having that much normal force. And if I invited you all to my house for a field trip and we all started standing on the table, probably at some point it's going to break. I don't think it would probably hold all of us. I don't even think we could all fit on it, first of all, but even if we could, I doubt if it would hold all of us. Eventually it would break. So the normal force is always going to be equal to the weight if it's a flat surface, until it can't hold it anymore, until it's just not structurally sound enough to hold it. All right, so how does that compare to friction? How does it relate to friction? So let's figure out, what is friction first of all? Well, primarily friction is a resistive force. It resists motion in most contexts. There is a way we can think about it actually causing motion. We'll talk about that next week. I don't want to confuse you with that too much today, but primarily we think about it as a resistive force. It doesn't let the surfaces slide on each other very nicely, or sometimes it won't let them slide at all. Friction is a resistive force that opposes the motion in most contexts. And again, you're familiar with that. In this curriculum, they usually abbreviate friction force or use the variable for friction force as F with an FR subscript. Personally, and our textbook doesn't usually add the R. Usually it's just capital F with a subscript F. Either way is fine. Now, when we talk about friction, there's actually lots of kinds of friction that we don't usually call friction. Friction is the reason objects stop moving. So if I roll a ball across the floor, eventually it stops. It doesn't just keep going forever because friction and air resistance slow it down. If I slide something across the floor, it doesn't slide forever. Eventually friction slows it down. The higher the friction, the faster it slows it down. The lower the friction, the less it slows it down. With these people pushing this car, they may have less friction because of the ice and the snow, so they may have a harder time getting traction. So they want that resistance to motion, right? They want their feet not to slide on the ground. They want their feet to stay stuck so they can actually leverage that push and make the car go forward. But there are some other kinds of friction we just don't usually call friction. What we usually call air resistance or drag is technically air friction. It's the air's friction against whatever object is moving through, or the water if it's dragged through water like a boat in water. That friction of the fluid against the object, we usually just call drag, or in the case of air, air resistance. But technically it is a kind of friction. For liquids or for other fluids, usually we think about it with liquids, but it could be any fluid. We can talk about viscosity and how, like maple syrup or molasses, it has strong intermolecular connections that make it flow really slowly. And that's the friction between the particles because of those intermolecular attractions. If you don't know about intermolecular attractions, it's kind of a chemistry thing. Don't worry about it. You'll learn it when you take chemistry. But they basically create friction between the molecules so that they flow slower in things like oil and molasses compared to things like water or alcohol. But while viscosity and air resistance and drag are technically friction, we don't usually call them friction. And so I just want you to be aware that you could call them friction. We usually just use those other words to describe it instead. So normally when we talk about friction, we're really usually talking about solid to solid contact, a solid surface touching another solid surface. And we're going to start with what we call kinetic friction force. Any idea what the first word kinetic refers to?
The objects are sliding against
Yeah.
each other.
Yeah, there has to be motion. If you've ever learned like potential energy and kinetic energy is the energy of motion, potential is stored. So kinetic friction means that they're actually sliding across each other. There's motion between the two surfaces. Now, what creates that friction? Where does it even come from? Well, when we look at like my table, for instance, it looks really smooth. And so it seems like if I want to slide this calculator across the table, I should just barely have to push it. But there's little rubber feet on the bottom of these calculators and it kind of sticks. Even though this feels smooth and the table feels smooth, there's something about these surfaces that gives it some grip. And so it doesn't quite slide as easily as I think it should. And it's because there's actually, if we look at it under a microscope, little pits and grooves and divots and bumps, and those little surface imperfections actually catch on each other and stop it from moving so easily. And then again, for those of you that have had chemistry, there's also going to be some polarity attractions between the protons of one and the electrons of the other, and creating those intermolecular attractions between the molecules that make up those surfaces. So all of those things are what create friction. You don't really need to understand the chemistry behind it, but I like to throw that in for those that know about that so you have a little bit of a deeper understanding. So that's where friction comes from. If the objects are actually sliding surface to surface, we call it kinetic friction because there is motion between the surfaces. Now there is an equation to calculate friction, and it's a pretty simple equation, and it's on the AP formula list. Friction force is equal to the coefficient of friction times the normal force. So that's why we reviewed the normal force here a few minutes ago. The coefficient of friction, the variable they use, is actually the Greek letter mu. It looks like a fancy U, or a U with a front tail on it. And so it's just a funky looking little U. We call it mu. In fact, you'll see if you Google friction puns and things like that, you'll see things about cats and mewing with their friction. But that coefficient of friction is called mu, or if the letter is called mu. And it's, in this case, they have a K beside it because if we're thinking about things sliding, we call that kinetic friction. If it doesn't slide, we call it static. So that mu depends. Is it sliding or is it not sliding? The number is going to be different depending on whether it's sliding or not. So for example, if I put my calculator on this folder, I can tip it up and tip it up and tip it up. And for a while, there's enough friction, it doesn't slide, but eventually it starts to slide, right? So when it's just sitting there, even as I tip it up, it doesn't move, it doesn't move, it doesn't move. That's considered static friction. It isn't moving yet, but then eventually it slides and then it's kinetic friction. Okay, so that's how we're going to divide it. And so here, that little K beside the coefficient of friction just means, oh, we're talking about how much friction there is between them when they are actually sliding. The normal force, the reason we think about the normal force instead of the weight is because the normal force is always perpendicular to the surface. And if I think about this, right now, with a flat surface, the normal force is the weight, right? I mean, it's perpendicular to the surface. So the weight would be straight down, the normal force is straight up. So those would be equal. But as soon as I start tipping it, now the normal force is perpendicular to the surface, right? But the weight is straight down. If the weight is straight down on the y-axis and the normal force is perpendicular to the surface, only the y component of the normal force is equal to the weight. So when we think about friction, it's not just the weight of the object, it's how much of that is perpendicular to the surface. So we have to use the normal force. So if we're talking about flat surfaces, the weight and the normal force are equal. If we're talking about angled surfaces, we have to use the normal force specifically, and it's just going to be how much of it is perpendicular to the surface. As I angle it, the normal force gets less and less and less and less and less. And eventually, if I have it purely vertical, there is no normal force. There's no way for this to have any friction when it's perpendicular. It can't stop it from sliding if there's no normal force. All right, so a little bit of a preview too of static friction there, but that's the equation, and let's practice it a little bit and see how it applies. That coefficient of friction, that little mu symbol, it's not something you have to memorize. It's different for every combination of surfaces. So if we look at this scenario or this table here, we've got wood on wood has a coefficient of 0.2, ice on ice 0.03, metal on metal if you use oil to lubricate it 0.07, steel on steel when you don't use oil 0.6. And so you usually look these values up or you calculate them. I had a few students come in during our Wellness Wednesday a couple weeks ago, and they actually calculated this value for coefficient of friction experimentally. They drug different objects across the ground and across tables, and they actually found out the normal force, and they found out the friction force and calculated the coefficient. And so these are just examples of ones that have been tested experimentally and determined. So you can see the one at the bottom, human joints and limbs. If you have a healthy joint like a shoulder or knee or hip joint, if it's healthy, then there's almost no friction. It's very low, 0.01 coefficient of friction. If you have damage like torn cartilage or like different spots on the bone that are rough because of an injury, then it won't be quite that low. So there's a little bit of variability there if you've had injuries. All right, so now let's actually start to apply this whole kinetic friction force. We've got a man accelerating a crate across a rough surface. So let's think about the free body diagram if this is the scenario. Someone unmute and tell me one force that would be on this crate that the man is accelerating. What's one force?
Normal.
I heard normal force. Okay, so we got the normal force of the floor pushing up. Somebody else unmute and tell me a different force. Sorry?
The push force, like of him pushing it.
Okay, the pushing force, how much he's applying or pushing with. So there's two.
And the
Any
weight.
other forces?
The weight.
The weight, gravity pulling it down. So the weight, there's three forces.
Friction.
Friction, since there's a rough surface, there must be some friction. So if we think about the forces in this example, we should have a normal force and a weight force. Here, instead of using F sub G, they've just used mg because that's how we calculate it. And then we've got our friction that's resisting the motion. And we've got our pushing force the person is applying to this crate. And if it's accelerating to the side, that applied force must be larger than the friction. And it said here the man was accelerating it. So since the man is accelerating it, we know that this has to be a larger applied force than the friction is resisting it. The two vertical ones cancel, but the horizontal ones do not. So then it says determine the net force in the X and Y directions. So what's the net force in the Y direction?
0.
0, yeah. The net force in the Y direction would be the normal plus the weight. The normal's up, the weight's down. They have to be equal because it's on a flat surface and this crate's not going to fly into the air or dig down into the ground. So there's no net force vertically. But there is a net force. Let's see if we can get this out of the way here. There is a net force horizontally. The applied force minus the friction force would be the net force. Questions about that idea? Again, separating horizontal and vertical. All right, just a couple more slides here to wrap this up, and then we'll talk more about static friction to close out our lesson. So here we've got a question for you to answer in the chat. A brick is sliding to the right on a horizontal surface. What are the directions of the two surface forces? And the forces they're wanting you to think about are the friction force first and the normal force second. So in this scenario, what would the direction of the friction force be with it sliding to the right? And what would the direction of the normal force be? When you know, just type your answer in the chat. You can just do A, B, C, or D. And we're getting a lot of votes for D. That is correct. we can see that if it's moving to the right, the friction would be to the left, making that movement harder. And then the normal force is always going to be perpendicular to the surface. Since it says it's horizontal, it would just be straight up. So D is the correct answer. Right, let's try a math one. If we have a 4 kilogram brick and it's sliding on a flat surface, and the coefficient of friction between the surfaces is 0.25, what's the size of the force of friction? Now, a real quick side note before we calculate this, you may notice this 0.25 coefficient has no units. If we look back on this list here, no units. The reason is, here's our equation. If I solve for this coefficient, U or mu equals friction force divided by normal force. If I'm taking force divided by force, I'm taking newtons divided by newtons. If I'm taking newtons divided by newtons, they cancel out. So when we calculate the coefficient of friction, it has no units. All right, so what is the size of this friction force? So given this information, go ahead and calculate what the friction force is and type your answer in the chat. All right, so I'm starting to see a pretty consistent flow here. Depending on what you use for G, it's going to slightly alter your final answer. But the mu is given, 0.25, so we just plug that in. But the normal force would be the same as the weight force. Since it's on a flat surface, the normal force and the weight force would be equal and opposite. And so the weight is mass times G. So if you use 10 for G, you're going to get a 10 Newton friction force. If you use 9.8, you're going to get a 9.8 Newton friction force. Quick reminder, as you're doing positive physics questions, you do need to use 9.81. In the questions, it says down there in the bottom of all the pages, 9.81, please use that for G anytime G is applicable. But here on this one, since it doesn't specifically say, either one would be fine, either one would be acceptable on the AP exam as well. Questions about this example? All right. Static friction. So I've already kind of introduced the idea. Static friction is just what friction's value is when it's not moving. So you're pushing, but it just won't go. It's stuck. You haven't been able to get it to slide yet. Or like I was showing you before, it's tipping, but there's still enough friction that it doesn't start to slide. It still just sits there. So that would be static friction. It's enough friction to keep it from moving. And then once it starts to slide, now it's become kinetic friction. And if you've ever noticed in real life, it's almost always harder to get something moving than it is to keep it moving. And that's not a figment of your imagination. That's a reality. The static friction force is typically larger than the kinetic friction force. And that is because when two objects are stuck or static, sitting still, not only do those pits and grooves and bumps and divots kind of lock into each other more, there's more time for those intermolecular attractions to build up as well. And so generally speaking, when things are sitting still, that static friction force is much larger. Once you get it into motion, those bumps and divots kind of bump off of each other, but they don't like interlock as much. And there's not as much time for intermolecular attractions to build up because it's moving. And so the different molecules are constantly being in contact with different molecules. And so kinetic friction is almost always less than static friction. There are a few real rare random examples where that's not always true, but you can always assume it will be in the kind of problems we'll be doing. And just so you can see a way we calculate it, the equation really is the same, but there's a little bit of a difference in the fact that instead of saying friction force is equal to the coefficient times the normal force, you'll often see it written as the friction force is less than or equal to that product of the coefficient times the normal force. Because let's think about it flat first. If I push with my pinky and I barely push, it doesn't go anywhere. So the static friction against my finger is little because I'm not pushing it much. If I push a little bit harder, the static friction has to be more. If I push harder, the friction has to be more. It's like the normal force. Remember how we talked about the normal force? Right now, it just has to carry my computer and my mouse and my tablet. But if I were to stand on it, then it has to provide more. If two of us stood on it, it has to provide more. The static friction is kind of the same way. It'll resist as much as it can until it just can't anymore. Eventually I push and it can't stop me, and now it's kinetic. Okay, so the static friction will just be whatever it has to be to resist motion until it just can't anymore. Just like the normal force will be whatever it has to be until it breaks. Okay, so it's the same kind of an idea. So sometimes you'll see it written as less than or equal to illustrate that concept, but it's caused by the same interactions, those same mechanical imperfections on the surface and those intermolecular attractions. So here is just an explanation of what I described. Could I get someone to read this slide for us to just touch on it one more time?
Sure.
Okay.
Should I start with imagine or?
Yeah.
Okay. Imagine pushing on a box until it moves. You can apply a small force, nothing happens. You apply more and more force until the box finally starts moving. This is the maximum amount of static friction. The friction can be less than the maximum amount or equal to the maximum amount, but never greater. The force or friction is equal to that at the instant when the object starts to move. Then what happens?
So after you've provided enough force, it eventually is going to start to slide, right? There's a limit. Just like there's a limit to the normal force of a table, there's a limit to the friction force between surfaces. And so the way we can envision that is actually to look at it graphically. The static friction force increases as we apply more and more force to the object. It's always going to be equal to the applied force until it surpasses that maximum. And so if we think about the graph, if I apply no force, there's no friction. If I apply 10 newtons of force, it applies 10 newtons of friction to stop movement. If I apply a 20, the friction is 20, it doesn't move. If I apply 30, the friction's 30, it doesn't move. If I apply 40, the friction's 40, it doesn't move. It just keeps matching it until it can't anymore. Once it reaches 40.1, or maybe even 40.01, whatever, once it surpasses that maximum, then it starts to move. And like we said, the kinetic friction force is actually less than the static friction force for almost all surface combinations. So once it starts to move, instead of just keep increasing to match it, eventually it starts to slide, and then you just have a constant friction force. Now, in reality, no surfaces are perfect. So you might, in reality, not have a perfectly constant friction force because there may be like a divot in the ground or something that it catches on. But if the surfaces are relatively constant and relatively smooth, it will be a same friction force as we keep sliding it across that consistent floor surface. So any questions about the connection between static and kinetic friction? So a common question, and we'll practice some of these next week, is what if I provide a certain amount of force? The question will ask, well, does it move? And what you're trying to figure out is the static friction capable? So they would have to tell you the coefficient of friction. You would just calculate, oh, what's the static friction? If the force is not enough to make it move, then it doesn't. You know, because when you calculate the static friction, what you're really calculating is that maximum value. If you take the normal force times the coefficient, it's telling you the maximum value that it can hold. And anything less than that means the object won't move. But anything more than that means the object will move. And then you have to switch gears and start thinking about kinetic friction instead. We'll practice some problems like that next week. But for today, That's all I have. Just wanted to get through those two topics. Any questions from you as we wrap up?
Is there any relationship between the static coefficient and the kinetic coefficient of friction?
There's not a direct correlation. So I think in my other notes that we'll look at Monday, I have a chart that shows them both comparatively. I don't have that open right now, but generally speaking, the static coefficient of friction is always a larger amount than the kinetic one. There are a few examples that are exceptions, but how much different really depends on the surfaces. So for some, it's almost, maybe like a 0.01 difference. And for others, it might be like a 0.5 difference. It just depends on what the surfaces are made of. So there's not like a regular way to determine it. It actually has to be determined experimentally. All right. If you have other questions you want to ask that are more individualized, you're welcome to stick around. But I'll go ahead and dismiss you for now. You got about 15 minutes left. If you want to jump in and look at some of those positive physics questions or start working on other work that you need to get done, you can do that. And if you have questions, stick around. But otherwise, I'll see most of you next week. I'll see a few of you tomorrow. So have a great day.